Welcome back. Today is lecture 18 and we shall continue on microwave MESFETs, gallium arsenide MESFETs. If you recall, we discussed about the basics of fabrication in the last lecture. We talked about recess gate, N plus contacts for source and drain. We talked about some of the steps of fabrication of gate aligned and self aligned process, and also the ohmic priority self aligned process. We shall continue from there, but we shall go into finer details of why is it necessary, for instance, to have that ledge. We did not even talk about ledge, but what is the ledge, that N plus ledge that you have that defines the recess in your gate, how critical it is for that to define the breakdown. We shall consider that, and then we will talk about the gate profile, the gate, how does the gate metal actually look like, a mushroom shape, T shape, etc. And then from then we will talk about the small signal model, we will talk about the noise model, we will talk about microwave power performance, Johnson figure of merit, etc. as we go ahead today in the next lectures. Okay. So if you go to the whiteboard here, you will see that the last slide of the last lecture was we had ended this in different types of recess gate, and I told that in some cases the gate to source distance is far, in some cases the gate to source or drain distance is not so far. There are different types of recess. We should spend a little bit of time in understanding actually how do people come up with this kind of designs and why it is necessary for the device performance. Okay. So as I told you, there are two kinds of wafers, one is epitaxial and one is ion implanted. Suppose I take the case of epitaxial wafer. Okay. Same concepts will hold true for ion implanted also, however we will talk about epitaxial here. So you have a semi insulating gallium arsenide substrate, okay, which is chromium doped, and then you have a buffer layer which is undoped, okay, and then you have an active layer, okay, which is your channel, okay, and this channel is typically doped in the range of 10 to the power 17 per centimeter cube, could be 3 into 10 to the power 17 or 5 into 10 to the power 17, etc. The stack is grown by say MBE or MOCVD. So these are techniques to grow epitaxial layers one atomic layer at a time. So you keep growing one atomic layer at a time, you keep growing, and then on top of that you grow a very highly doped N plus layer. Okay. Now of course the gate cannot sit on the N plus layer, so you have to etch the gate away. So what happens is that this structure will now look like you have an N plus layer, okay, then you have an N plus layer, correct, which is etched away so that you can put the gate here, okay, and this is your the channel layer, okay, and this is your buffer layer, and this is your substrate, correct, of gallium arsenide. Now of course people also do a recess. So people you can do a recess in the sense that you can etch this part away and then you can put the gate as a recessed here. Now this helps in reducing the contact resistance, right. However, this spacing defines the breakdown to first order. Okay. What it means is that if I go to the new diagram here, if you have a gate, I have not shown a recess here, but we can show a recess subsequently. If your N plus is here, okay, N plus is here, versus this is drain, this is source, versus another structure where you have a gate here and the drain is far away, this is N plus and this is drain. Okay. Source side I will not care because the source side does not actually influence the breakdown. In fact, this should be as close as possible. Okay. That helps you in reducing your source excess resistance, and if you reduce your source excess resistance, it helps improve your extrinsic transconductance. Extrinsic transconductance is the as measured transconductance. Okay. Intrinsic transconductance is the transconductance of the pure device below the gate. Okay. So anyways, you can bring the source, you should bring the source as close to the gate as possible. It helps improve the injection of the carriers, helps improve the source excess resistance, and hence improves the extrinsic transconductance and so on. Now what happens is that in this case the breakdown will be too low because your N plus layer is very close to the gate metal. So you think of this N plus is also like a highly doped layer, so it is not metal but it is almost like highly conducting. So very close, you will break down sooner, and you have to remember that this is an active N doped layer here. Okay, it is an active N doped layer, and you are going to drop the field between the gate and the drain. So when you have a highly conducting layer here, you are not going to drop the field as much, but here you are going to have a larger spacing, so your breakdown voltage will improve here. However, in this case your breakdown is great, but your cutoff frequency will be kind of lower. Why? Because between the gate and the drain you have a large spacing, so your drain excess resistance is large. Whereas here between the gate and the drain you have very narrow spacing, so your drain excess resistance is very low and this will help improve your cutoff frequency, okay, but also it will reduce your breakdown. So there is a trade off that you have to pay anyways. So how far you should have the ledge is something, it is a design parameter, what kind of frequency, cutoff frequency you want, what kind of breakdown you want, both of them matters, okay. But this is a single recess, this is a single recess because you have just removed the N plus layer and put down the gate there. People do a double recess, which is what I have already showed you. This could be a double recess for instance, okay, in the way that you have a, what you can do is that you have the first recess which is your N plus, correct, your N plus, and then you have another recess here where you put down the gate, right. So this is a double recess, one recess is this and the other recess is this, you see, maybe I can choose a different color here. So this second recess is this is the second recess, okay. So this recess helps improve breakdown voltage, alright, and have a better channel control, so better GM as I already told you. This spacing will also dictate your breakdown, but again you do not want it to be too close or too far, it depends on the design that you have, okay, it depends on the design that you have. But double recess is all about improving the trade off, the breakdown and the cutoff frequency, breakdown and cutoff frequency, breakdown and GM, okay, that is all the trade off is, the double recess. Now while we are here, the gate metal that you are putting down, okay, the gate metal actually looks like that, right, it is a slab, it is a metal slab. So this is your cross sectional area of the gate, so this depends on the, this is your gate length by the way, correct, this is your gate length, the length of the gate, and that is one of the most crucial parameter because gate length directly affects your transconductance. A lower gate length helps improve your transconductance, which is good for noise, which is also good for gain, good for higher frequency performance, etc., etc. So this is your gate length, this is the thickness of the gate metal, right. You can use different, of course you can use different stack, you know, titanium, the first layer could be titanium, the second could be platinum, the top could be gold, whatever, but the total, I am talking about a total gate here, that is your thickness T, that is your length L here, and this is your W, which is the width of the gate, okay. The width of the finger, this width of the finger will determine how much current you carry, the current that you carry per finger. You can have multiple fingers, of course, you know, 5 finger, 6 finger, 10 finger, etc., etc., that will keep on increasing the current, overall current, and current is, of course, your design depends on how much current you have in the device. So the W defines your current, it also comes in noise by the way, we will see later on. The gate length defines your gain, noise, high frequency performance, etc., etc. The thickness of the gate metal along with the gate length and the width of course defines the resistance of the gate metal, the gate resistance, and that is a very crucial parameter. As we will see, gate resistance needs to be as low as possible. Gate resistance needs to be as low as possible because a low gate resistance is a low parasitic, you know, it is a parasitic essentially. A low gate resistance is highly desirable for better noise, which means you need no noise, low noise, and also for high cutoff frequency called Fmax, oscillation frequency. I will come to that very soon, okay. To improve the high frequency performance you and also to improve the low noise, to make the low noise lower, your gate resistance should be as low as possible. Now if you look here, what can we do actually, okay. So if I look at the gate resistance, so maybe I can use whiteboard here again, okay. So you have a gate bar something like that, okay. And as I have this is your gate length, this is your gate width which dictates the current, also affects the noise, gate length, and this is your height of the metal. Now this see this cross section area, okay, the gate resistance, you are looking at the gate resistance like that by the way, okay. Okay, so the cross section is T into Lg, correct. So your gate, if your metal, this is a metal stack, it could be titanium, aluminum, gold, titanium, platinum, gold, etc., etc., not titanium, aluminum, but titanium, platinum, gold, or whatever, tungsten. The total resistivity is suppose rho, which is, you know, which is not something you can change much. Then rho into L by A is the total resistance, you know, and rho, L here in this case is W, okay, W divided by T into Lg. So you see, to reduce this gate resistance, you have to reduce W, but you cannot reduce W arbitrarily because your W dictates the current. So, if as long as you want a certain current, you cannot do much about it. You can increase LG, increase the gate length to improve the or to lower the gate resistance. However, if you increase LG, then you lose out or you miss out on the high frequency advantage, correct. A higher LG is not desirable for both for noise as well as for high frequency performance, for gain, etc. We said that we need low LG, we need the gate length to be as low as possible. So, if you give a lower LG, if you increase the LG, then that defeats the purpose. So, your LG is pretty much fixed. Okay. So, for instance, you might have 0.5 micron as your LG, which is a 0.5 micron gallium arsenide MESFET technology, for instance. Okay. So, you fixed, then the only thing you can play with is T, which means you increase the thickness, but you cannot increase the metal thickness arbitrarily, because then there is a stability of the mechanical stability of the metal. You have a 0.5 micron here. If you make this like 5 micron, then it will be like a tall slab. Okay, it will be like a tall slab like that, and it can collapse. So, that's a problem. So, one way to avoid many of these problems and still improve the gate resistance or lower the gate resistance is using a mushroom shaped gate, something like this. Okay, where the bottom of the gate is, of course, this point is still LG, it is defined the foot, this is called the gate foot. Okay, this is called the gate foot. The foot of the gate is still LG, which could be say 0.5 micron. However, the top of the gate, which is called, this part is called the gate head. The gate head could be wider, this will lower your gate resistance, because you have a very large gate metal which is very wide, So, your total gate resistance is because of this line and also because of this line, right. So, the total, so you have something like that, right. So, this defines the gate foot. So, your 0.5 micron is not compromised, this could be very large, and because this is very large, your gate resistance, when you do this, your total gate resistance, because the cross section area is very large, so your gate resistance comes down. Okay. However, this should not collapse. So, the mechanical stability matters, you cannot have arbitrarily large head because your gate foot may not be able to sustain it. Now, another problem here is that not problem, but you need to be aware of the challenges, is that whenever you have a gate head like that, it will start coupling capacitance CGD. The gate drain capacitance will be more, because your gate is now closer to the drain edge as opposed to not having this head. So, what I mean is that, suppose this is your gate, this is your drain, coupling between them is certain value CGD. The moment I have a gate head something like that, then the coupling, the gate and drain has come closer. So, your gate drain coupling has become stronger. So, your capacitance is increased. So, any increase in the gate drain capacitance is an increase in the parasitic overall capacitance. Okay, overall parasitic capacitances. So, you have an increased gate drain capacitance because of this head. So, your and so your overall cutoff frequency, I will come to cutoff frequency, will suffer, it will become lower slightly, but your gate resistance also becomes lower, and which helps in noise and which helps in the other cutoff frequency called F max. So, it is a trade off ultimately that you have to pay. Now, this is air, sometimes it can collapse if it is too large. So, sometimes people may fill it with dielectric also. So, to support the head, the support, it could be silicon nitride dielectric to support the head, but then dielectric constant epsilon of the silicon nitride will come into picture. So, your cutoff frequency, whether it is FT or F max, I will come to that, will significantly become lower again, but it may not matter if you are looking to operate your device at lower frequency like 1 or 2 gigahertz. Okay, you want to power, then your silicon nitride might be still okay, or maybe 900 megahertz, 800 megahertz, etc. But if you are going to higher frequencies, 6, 10 gigahertz, etc., then you need to have this air actually. Okay, so this is the ledge, this is your N plus. Okay, this is your double recess actually. This part is your double recess. This is your this ledge could be your mildly or slightly mildly doped N minus region. Okay, this is a generic picture, by the way. Here, this particular picture is a generic picture applicable to MESFET as well as HEMT. In this case, this channel might mean, this cap layer might mean an L-gas cap, which could be in a HEMT. Okay, so this could be a HEMT for instance, but this concept holds true for even MESFET. So, this is called a mushroom shaped gate, okay, or a T shaped gate you can say, because it looks like a T. Okay, so T shaped gate or mushroom shaped gate helps improve the gate resistance, lower the gate resistance, and this is useful for a lot of applications. Okay. This is a scanning electron microscope image of a real fabricated mushroom shaped gate with a gate recess. You can see this recess, correct. You can see this second recess actually. This is the first recess. This is the first recess. This is a scanning electron. This is 100 nanometer. You see, this much is 100 nanometer. You can see that. So this gate could be 100 or 200 nanometer. Okay. This is the recess, the second recess, and this is the mushroom shape. You can see that. This is the mushroom shape. This is image is taken from a paper published 10 years back. This particular image is for a pseudomorphic HEMT, but does not matter. Even for gallium arsenide MESFET, this is a gallium arsenide pseudomorphic HEMT, but even for gallium arsenide MESFET, the image would look very identical, almost very similar, because you have the same concept of a gate recess and mushroom shaped gate. Okay. So then we move to small signal. Small signal models are very pertinent for high frequency application, although we should remember that in microwave frequencies we have to use the concept of transmission line, but at lower microwave we can still use lumped elements to a certain extent, and small signal models are still very valid because for a certain given bias condition we can still treat these capacitances, resistances as lumped elements and build a small signal model. However, when we implement them or when we have the actual device, most of these resistance capacitances could be transmission lines. What is transmission line? We will come to that towards the end of this course when we talk about microwave engineering concepts for devices. Transmission lines are like distributed. Your capacitance cannot be just one lumped element, or a resistor could be one, it could not be one lumped element, because the wavelength of your microwave signal approaches the dimension of the capacitor or the resistor or the inductor. So you cannot use the lumped element approximation. You need to have a distributed resistance, distributed capacitance, distributed inductance. So transmission line comes into picture. Anything that in which the microwave signals will propagate with a ground inference reference plane and then a signal line, that is a transmission line. So although we have a transmission line concept, we still, to a reasonably good accuracy, we can still build a small signal model at a given bias. Okay. So a small signal model of a microwave transistor, in this case a MESFET, is very important, and if you think this image looks little bit busy or a little bit more tricky, it's actually not, it's very simple. So we can go one by one as to what. So this is your physical device model where different resistances and capacitances are shown or represented, and this is your model that you are using. Once you develop this, once you have this model, you have experimental techniques using a vector network analyzer. It is an instrument called vector network analyzer to measure something called S parameter. Again we will come to S parameter definition towards the end of this course when you talk about microwave engineering. So there are things like S parameter, scattering parameter, that you have to measure, and depending on different conditions, different calibration structures, etc., you can measure these S parameters, and from that you can extract out these different capacitances or resistances. Different capacitances and resistances can be extracted out from these lots of S parameter measurements that you do, with the output open, the output short, the input open, input short, etc., having a through line, having an open line, short line. You do a lots of permutation combination, you find out different S parameters, and from there you are able to extract out these different small signal components. You can build this small signal model for your particular MESFET or HEMT or any transistor at a given bias condition, at a given drain bias, at a given gate bias, because the moment you change the gate bias or drain bias, most of these parameters of capacitances, resistances, especially capacitances, could change. So your small signal model is defined at a particular bias, and the small signal model is very useful in this high frequency analysis, as we will see throughout the course, of course. So you can see here that whatever is around the gate is your intrinsic device, this part for instance is your intrinsic device, everything else is extrinsic. So you can see that there is a source excess resistance which is extrinsic, the drain excess resistance, this is the dropping, the voltage resistance drop between the gate and the drain, gate and the source. There is of course contact resistance here, there is contact resistance here. In this particular image the contact resistance is clubbed with this, in this contact resistance is clubbed with this. There is a gate resistance, this is the gate metal resistance that we have discussed in length. CGS is a very key parameter, it is one of the most important parameter, it tells you about the coupling between the gate metal and the source. The channel which is towards the source, okay, it is coming towards the channel, okay, but it is towards the source. So you are coupling with the gate with the source, but through the channel in a way, okay, that's CGS. Alright, this R in is basically your input resistance, it is basically the resistance to the gate. So if you have a barrier layer or an oxide layer or something that is resistance to that, so in general you have a certain barrier layer, for instance your capacitance is across the barrier, your resistance is also across the barrier, that is why this input resistance and this capacitance are kept in parallel. However, in certain textbooks I have seen that people also use this resistance in series with the your CGS or the gate source capacitances, okay. But more or less the models work out similar, I think, at the end all of it. Then there is this gate drain capacitance, very important. It is the coupling between the gate metal and the drain side, okay, the drain side of the channel, okay. At this point, once you have the source the drain excess resistance, at that point where it terminates, your drain will couple to the gate, and that is your gate drain capacitance. RCH is the channel resistance, 2DG has its own resistance, so that is your R channel, and that is in series with the CGS, of course. GM VGS is your drain current essentially, okay. Your VGS is dropping here, which is your gate voltage is dropping between the gate and the source. This is your source. So, you are coming from the gate resistance is coming at this point, at the gate point, and at this point, which is your source point, this is of course source resistance, this is your drain resistance, of course, RD. At this point you have the drain out excluding the resistance, at this point you have the gate, and at this point you have the source. Between the source and the gate you have the CGS, which is between the gate and the drain you have CGD, which is the gate drain capacitance. Of course, parallel to CGS is your input resistance, which is here, and with series with them is the channel resistance here, which is this, correct. And GM VGS is actually the drain current that is flowing, okay. So, GM times VGS, which is the transconductance times the input voltage, is your output current. So, this is like the drain current that is flowing between the source and the drain, this is your drain, remember. So, this is flowing between source and the drain. This RDS is basically your drain source resistance. You can think of this as the output conductance, okay. Ideally it should be infinity. So, if you have a something like that, then this is your resistance should be infinity. But if you have a non-saturating current something like that, then you have a finite value, which is your RDS, okay. CDS is drain source capacitance, people can neglect that to some extent, but yeah, it is alright, there is a drain source coupling, but that becomes important only when the channel is pinched off, otherwise the channel is conducting and there is barely any capacitance between the gate and between the drain and the source. So, when it is pinched off, there is a depletion between the gate and so between the source and the drain, and so the source and drain can couple across the depletion region, and that is why then it becomes important, okay. C parasitic is basically just a coupling between the metal to metal here, but again many textbooks can kind of neglect or ignore it. So, this is your small signal model. Now, from this small signal model actually you can derive and find out the expression for the cutoff frequencies. We will not do that, but I will tell you how they do it, the cutoff frequency. But before that, it is important to talk about the cutoff frequency, and even before that it is important to talk about these different components which I already did, but nevertheless I will repeat some of these things here, okay. For instance, this is your input resistance, as I told you, this is your gate leakage, and in general it is infinity if your gate leakage is 0, but practically gate leakage is not 0. So, the derivative of the gate leakage with respect to the gate voltage, the inverse of that is your gate resistance or your input resistance, and it can be very high, mega ohm, okay, or giga ohm, okay. This is your gate channel capacitance, as I told you, gate to source capacitance through the coupling through the channel. This is your gate to, where is it, this is your gate, actually this is gate channel capacitance has two components, one is gate source and one is gate drain, okay. Remember, gate to channel capacitance actually has gate to source and gate to drain. So, the gate is coupling to the source here, gate is coupling to the drain here, okay. So, the gate is coupling to both source and drain, that together is called the gate capacitance, gate channel capacitance. So, gate channel coupling towards the source and gate channel coupling towards the drain side, they are CGS and CGD, okay. Gate source and gate drain capacitances together they make the gate capacitance. This is excess resistance, this is source excess resistance, that is drain excess resistance, this is your gate resistance, alright. This is a very important parameter, this is your extrinsic GM, that is the GM that you are measuring in your instrument, or that is what you are going to get in your circuit. This is your intrinsic GM. Intrinsic GM is the true GM that of the device that should have been there if hypothetically the excess resistances were not there, okay. So, what is happening here is that if I just take a generic transistor, you have a gate here and then you have a source here, a drain here, it could be MESFET, it could be MOSFET, HEMT, MOTFET, whatever it be, okay. You apply some gate, the source is grounded of course, so you have a gate, some VGS you are applying, some gates, and this is grounded, some gate voltage you are applying, so there is a gate source voltage drop, but not all, and then this is the current that is flowing ID, okay, ID. Not all of this voltage of applied voltage is actually between the source and the gate, because there is an excess resistance here, okay, and that also includes the contact resistance to some extent. So, there is an excess resistance here, some voltage is dropping here, correct. So, ID, the current that is flowing, times RS is the voltage that is actually dropping on this excess resistance. So, the true voltage that the gate actually sees is not VGS, right, but it actually VGS minus ID times RS, okay. This is your applied voltage, alright, and this is your voltage that is actually seen by the gate. This is the voltage that is seen by the gate. So, I can call it VGS prime, okay. Voltage that is seen by the gate, really the voltage that is seen by the gate is this, the voltage that you are applying is VGS. So, VGS minus this drop gives you this. However, the drain current ID is nothing but GM times VGS prime, because whatever is truly dropping on the gate to source, the true VGS, which is this is your true VGS that is dropping, that VGS times GM gives you the current actually, because not GM times VG, because the entire VG is not helping you get current, part of that is dropping unnecessarily in the excess resistance. So, only this is dropping there. So, this is your applied VGS minus the drop, which is your GM VGS prime times RS equal to VGS prime, correct. So, your VGS is equal to VGS prime into 1 plus GM by RS, alright, 1 plus GM by RS, okay. So, from there actually you find that this extra factor is coming there, no, that defines your this part. So, your actual GM intrinsic, which should have been the true GM, is divided by 1 plus GM into RS. So, the source excess resistance actually lowers the overall this is the total measured transconductance or the actual transconductance that you will get in your device, which is lower than the intrinsic transconductance. So, the source excess resistance should be minimized, it should be lower, and that is why the source should come as close to the gate metal as possible. If the source comes to as close to the gate metal as possible, then your RS will be minimized. Of course, it should not significantly increase your gate to source capacitance, otherwise you will lose out on the performance advantage, but a lower source excess resistance helps you get a better extrinsic or as measured transconductance in your device, okay, in your device. So, this is a very important point that we should remember in mind. Drain excess resistance does not affect your extrinsic or as measured transconductance. Your as measured transconductance is affected by the source excess resistance only, and that, okay, of course, will include the contact resistance also here, but it is on the source side that affects your transconductance, the measured transconductance, just like your drain side affects your breakdown, not your source side. So, similarly the source side will affect your extrinsic transconductance. So, I hope this entire picture of the small signal model is clear here. So, we shall end lecture 18 here today. So, we have talked about the small signal model, and we have talked about the gate recess, the mushroom gate, the gate resistance, and the fact that single recess and double recesses are necessary, and these are very important concepts not only for gallium arsenide MESFET, but also for gallium arsenide HEMT, gallium nitride HEMT, etc. So, this is generic for all kinds of transistors, although we are emphasizing here on MESFET. Okay. In the next class there are 2 more lectures on gallium arsenide MESFET, 19 and 20. We shall start about a cutoff frequency definition, Johnson figure of merit, what kind of device parameters are desirable for power amplifier, what kind of device parameters are essential for low noise amplifier with respect to gallium arsenide MESFET is what we are going to discuss in the last 2 lectures, 19 and 20. Okay. So, thank you for your time, we will meet you again.